Okay, so I'm Axel Mertens. I'm doing a PhD at COSIC, KU Leuven, focusing on MPC and FHE.
Yeah, I'm Sergi Rovira. I'm doing a PhD at the University at Pompeu Fabra, and I'm focusing on FHE and post-quantum lattice-based cryptography.
Okay, then I'll share my screen and start the presentation. Hopefully everyone can see this.
Yeah.
All right, good. So I'll be talking about our paper today, the convolution-friendly image compression in FHE. This is joint work with Giorgio as well, who won't be presenting, but he's here, so we can ask him questions. All right. Okay, good. So the motivation behind this is that we want to do image processing on a server where the server doesn't know the image and the client may or may not know what the server is doing on it. So we want to add compression to this because we want a more efficient data transfer, which is often a bottleneck in practice. And we focus for the processing on convolutional filters, which is a basic technique that can do pretty basic filters, but still has its uses in practice. So this has applications in cloud image processing and also in secret satellite image search. So what has been done before in the literature? In the compression side, there is ciphertext compression, which I want to mention, but it's actually completely independent of what we're doing. It's something different. This is just once you have a ciphertext, making it smaller, basically. So this can still be combined with our technique. What is more relevant, though, is this paper by Fleischhacker, Larsen, and Simkin from Eurocrypt last year. They used invertible Bloom lookup tables for compression and decompression, but it should be noted that they cannot do a encrypted decompression. When they do a decompression, they have to do a decryption as well. Also, we have found that their technique only works for very sparse data. On the image processing side, however, there is the famous example of Sama. They did encrypted image filtering, so they also use convolutional filters using the concrete library. Our technique of processing is pretty similar to theirs, but they do not offer compression. Okay, so what is the pipeline we have in our setting? So we start with a client that has its image. The client will compress and encrypt that image, and then it can be sent over to the server. The server then, while it's encrypted, decompresses the image. So then he's left with just an encrypted image on which he can do some processing. Then again, compress it homomorphically, so still in the encrypted domain. And then it is sent back to the client that can then decrypt and decompress it. So that's the setting we're working in. The metrics we are going to use in this paper are the structural similarity index. This is a metric for image quality that is mainly based on human perception. It is also very good at spotting blockiness, for example, which is a very big, important thing for the techniques we're using. If the structural similarity index, or SSI, is larger than 0.9, we say that it's very good quality. And if it's larger than 0.95, then it's a very high quality. In practice, you won't be able to tell the difference unless you really zoom in pixel by pixel. The second metric we use is a compression ratio, which says how many bits are needed to represent 100 uncompressed bits. It's pretty straightforward. All right, so we base our technique on JPEG, which is a commonly used compression standard. JPEG is good for natural images, which means that it won't be able to handle graphical images or with like straight edges, discrete pixels. It won't be able to manage that very well, but actual pictures of landscapes and portraits, whatever, that's what it's good at. It's also called a lossy compression, which means that if you compress it and decompress it, the result will be just slightly different from the original, but hopefully the slightly different is similar enough that it's acceptable. Another attribute to JPEG is that you can choose the degree of compression, which is very nice. So there's a trade-off, a parameter built in that you can choose between quality and compression. It is based on the discrete cosine transform to transform the image into the frequency spectrum, and then it uses Hoffman coding to actually compress it. Okay, so let's go over the steps of how JPEG works. First, we split every image into 8x8 blocks. So then what you get is this matrix on the side here with values for each pixel between 0 and 256. Then the next step is to level it, which means we just subtract 128 from it so that the values are centered around 0. The next step is to do the discrete cosine transformation. So this transformation can actually be done with just 2 matrix multiplications from the DCT matrix. And then we get floating point numbers in the matrix. In this matrix, the top left element signifies the lower frequencies, and the bottom right is the higher frequencies. The next step is quantization, where we divide every pixel individually by a specific different value. This value is then summarized in a quantization matrix, which is standardized, and there is one good standardized quantization matrix that we find from the literature. So that's the one we use. And this matrix is actually also the reason we use 8x8 blocks, because the most standardized matrix is 8x8. So then we divide and round, and we get a lot of zeros in there. These zeros are centered around the higher frequencies, which is important because that's what we'll use to actually compress the data. So the next step then is to turn a matrix into a vector with the zigzag function. So the zigzag flows like this, which is very nice because then the zeros that we expect on the bottom right are all at the end of the vector. When we have that vector, we can finally do an encoding. Everything up till now has not done much compression yet, but the encoding will take care of that. So what is encoding actually? In lossless encoding, such as Hoffman, which is the one used in JPEG, data compression uses predictability in the data such that the entropy of the data increases with compression. So, for example, in the English language, an E is expected a lot more than a Z in a random word. So in that case, an E will be presented very shortly with 1 or 2 bits, and the Z or an X will be presented with 5 or 4 bits. Then on average, you will get compression because the shorter symbols occur more often. So the thing about that is that you then, to do such a type of compression, you do have to construct the code specifically for the data. So for English or for French or for images, it's all different codes. Even book to book, it would be different. So you have to construct the code, which is expensive. And also, if you wouldn't do that, the compression would be weaker, of course. Another issue with that, for FHE at least, is that it gives a variable length code. And this is very annoying for FHE, where you cannot do branching of any type. So a summary of what JPEG was. So we split it into 8x8 blocks. Then we level every value within these blocks. We apply the discrete cosine transform, which is just two matrix multiplications. We do the quantization, which is one element-wise matrix multiplication with rounding, which we actually wouldn't do in our scheme, but more on that later. And then the lossless encoding in the JPEG version, that would be Huffman. So why is this a lossy compression scheme? The loss happens in the quantization where we round down. All right. So how do we combine this with FHE? The thing is that compression schemes generally have a bad worst case behavior. So if every symbol or if every letter in a sentence would have the same probability of occurring, then you cannot compress it much. Also, homomorphic encryption intrinsically creates the worst case behavior because it is very hard to do conditional branching. It's too expensive in FHE. And it also would defeat the purpose often of doing FHE. So we cannot do variable length coding. Another thing we have to look out for is for privacy that we require within each block to have a constant compression factor. As you can see in the image I included below, the image on the right would show the information leakage if we knew only the compression factor of each block. So knowing nothing except for the compression factor, we can still kind of make out the silhouette of the hat, the silhouette of the lady. So that's not good for privacy reasons, obviously. So which solution do we propose for this encoding? We just cut off a constant number of ending zeros. So on average, we found that we can cut off between 30 and 40 values out of 64 because a block has 64 pixels. And this is, of course, very efficient to do. You just throw away the values pretty much. It's constant time and it's constant compression. The thing I should mention, though, is that sometimes this can result in cutting off a value that is not zero. So that's in theory not desirable. But we have found that this has a very limited effect on the actual result. So we can allow it. Then how do we do the image processing? There are two types of image processing that we are compatible with in our method. The first one and the easiest one would be pixel-wise processing. So this is absolutely very basic operations such as inversion, brightening, darkening. So you do each pixel individually. You scale it or you add a value to it without looking at the neighbors. So this is very easy because then you just need clear or secret multiplications or additions based on whether what the server does is actually secret or not. The second and slightly more complicated option is to use convolution filters. So then you usually have a 3x3 filter or a kernel that can be used for different tasks such as edge detection, blurring, sharpening, etc. So in that case, you just need, if what the server does is clear, then you just have clear multiplications and additions. Okay. The problem, though, is that for these convolutions, you do need the neighboring pixels. So the main issue then is over the different blocks, it's hard to find the neighboring pixel sometimes. So what we do is that we can split our image into 6x6 blocks instead of 8x8. And then we pad these 6x6 blocks again with the neighboring cells. And then we get an 8x8 block again. But the issue is then, or the downside is that now we have only 36 useful points out of 64. So this will bring down our compression ratio. Up till now, I've only talked about 8x8 blocks because these are the most well-studied quantization matrices. However, there is one standardized video compression scheme that uses a 16 by 16 quantization matrix. So we also tried out our algorithm at that size. We have found that the image quality is slightly less, but there we can achieve much more compression. Okay, now I will give the word to Sergi.
Thank you, Axel. So as Axel mentioned, we use FHE, and I will give a very quick recap. I assume that most of the audience already knows this, but FHE allows us to do arbitrary computations over encrypted data without using the secret key. So, for example, we can have two ciphertexts encrypting one message M1 and another M2, and we can do some kind of operation here represented as a triangle. We can think of this as an addition or a product, and the result should be the encryption of the operation as if it was done directly on the underlying plaintext. Though another way to think about FHE is it's a technology that allows us to do this commutative diagram, this diagram commutative. So if we start in the upper left corner and with some ciphertext, then we can either go down and use a secret key to decrypt and then apply a function over this plain text, or we can start with a ciphertext and then use the evaluation function of the FHE scheme to homomorphically evaluate the ciphertext and then do the decryption, and the result should be the same. So state-of-the-art schemes at the moment are mainly four. We have BGP, BFP, SIG-EKS, and TFHE. And for this work, we focus on SIG-EKS. So we will not go over the properties over the whole workings of SIG-EKS. We will just gloss over the properties that we care about for our work. So the first one is native support for floating point numbers. Then we have great packing capabilities in the sense that we can pack multiple floating point numbers into a single ciphertext. And we can also have SIMD manner operations in the sense that we can operate over all these floating point numbers directly in parallel, doing operations over to ciphertext. So the first property, native support for floating point numbers, what it allows us to do is to implement JPEG, the regional JPEG in the homomorphic domain without many changes to the algorithm. We only change the encoding by the encoding that Axel explained. Then the packing capabilities allows us to represent encrypted images in a very compact way, which I will explain next. And finally, the SIMD operations allows us to perform the image processing that Axel explained very efficiently. So regarding packing capabilities, so imagine that we have an image, okay, represented by this matrix. What we do is we consider 8 by 8 blocks of this image. And we think of this image as being this collection of blocks. Once we have this collection of blocks, what we do is we take, we consider the ith position of these blocks. So for example, the first position, it's represented here in green. So we take all the first positions in each block and we pack them into a single ciphertext. And we do the same thing for all the positions until we have the final position. So we have an image for us is actually a matrix of 64 ciphertext. So this way of encrypting an image allows us to do the following. So remember that our encoding is actually cutting off a few zeros at the end. So the number of ciphertexts that we need to send to the server for processing is actually 64, which would be all the ciphertexts that we have with the previous encryption, minus all the zeros that we have removed. So this is the number of ciphertexts that we send. Moreover, since what we do is pack the positions, so we can encrypt multiple images using the same number of ciphertexts, because the only limitation that we have is the size of the ciphertext, and this depends on the parameters of the FHE scheme. So if these parameters are set correctly, then we can pack as many images as we want. And this, for example, is very useful if we consider images of color, where we have multiple colors, or we just want to pack different images into the same number of ciphertext. And finally, this packing allows us to do the operations that Axel explained, the pixel-wise operations and convolutions, in a parallel way, because when we compute, we are actually modifying all the blocks in the same time. So let's go over the implementation and performance. We have chosen to use the implementation of ZKKS offered by OpenFHE. We consider a level approach, so we don't do any bootstrapping, and the maximum depth that we need to perform our experiments is 9. We select standard parameters for 128-bit security, or also set by OpenFHE. And the client and the server are simulated using a relatively powerful desktop as specified here. So the settings that we have considered are 4. So we have pixel-wise processing. Remember that this means that we are operating with individual pixels and on blocks of 8 by 8. And then we do convolutional processing. In this setting, we actually consider blocks of 6 by 6, and then we expand them to 8 by 8 by replicating some of the positions. And we do the same thing for blocks of 16 by 16. And these sizes are marked by the standard DCT matrices, as Axel explained. So here in this table, we present our timings. These are timings for 1 8-bit grayscale images. It's actually an average over multiple images. We don't consider colored image here, but we could do it using the packing, as I explained. And as you can see, most of the time it's spent in decompression and compression. The processing is quite fast. And the SSI, as you can see, most of it is over 90. So we can actually have a very high SSI with a good compression ratio. Just to clarify a few things. So if you look closely, the compression sometimes takes a bit longer than compression, and this might be surprising. And this is because when we decompress, we actually need to add the zeros that we have removed, and this is some extra work that the server needs to do. Yeah. And so to conclude, we want to consider a few future work. So there are 2 main points. First is that in our paper, we say that entropy encoding is not actually practical in FHE, but we don't provide any proof. This is something interesting to formally study. And the other is, of course, doing more complex image processing as object detection, face recognition, and others. Yeah, and thanks a lot for listening. Here are our contact details. We posted the paper in ePrint. It's under submission to ICIP. And you can also find all the code. And if you want to produce any demo, it's available in our GitHub. Thanks a lot.